Okay, so thank you everyone for joining. We're just coming up to after the hour, so we'll just kick things off. Today, I am delighted to introduce our colloquium speaker, Dr. Meredith MacGregor. Having completed her PhD in 27 at Harvard University, working alongside David Wilner, she followed this up with an NSF fellowship at the Carnegie Institution in Washington. Afterwards, she moved to Boulder, Colorado, before recently assuming her current position at Johns Hopkins. Her research interests exploit multi-wavelength observations of protostellar disks to investigate the formation processes and habitability conditions of planetary systems. She's also busy as a deputy PI and PI of the Far Infrared Spectroscopic Space Telescope and the Early Star and Planet Evolution Explorer, respectively. Finally, I should mention that Dr. MacGregor is a committed advocate of women in science through her various outreach efforts. And today we are also ready to be inspired as she tries to answer the question of how to form a habitable planet. A tricky task, but you have an hour.
Great. Yeah, there was some terrible feedback there for a second. Okay, so grand title. Clearly, I am not going to answer that entirely in 1 hour, but we'll do our best. So let's get started. As Callum helpfully nicely introduced me, I have been a professor at the University of Colorado Boulder for the last 4 years, but as of August, I am now back on the East Coast at Johns Hopkins. So it was very nice that I didn't have to fly out here. I could just drive up. It was lovely. Okay, so before I launch into science, I always like to start my talks with an acknowledgement of all of the wonderful people that I get to work with as a professor, because much of what I get to show you is the work of my students and postdocs, who are all amazing humans. So here are all of their names at the top. Right now, I have 4 undergraduate students working with me, 4 graduate students, a postdoc, and then there's been a number of alumni who have come in and out of the group and are now off doing all sorts of cool things. Here is our original group photo, which I like to show because I started as a professor in January of 2020, which was perfect timing. So most of these people all joined the group and we worked together remotely via Zoom for 1.5 years or 2 years before I actually got to meet like my first grad student in person. So here we are. And our group works pretty broadly on all things related to planetary systems, how they form, how they evolve over time, and whether or not they may or may not be habitable. Okay, so a quick primer on planet formation so that we're all on the same page. This is our overarching picture of how we think planetary systems form. We start with a giant molecular cloud. Pieces of that cloud become overdense and they collapse to form new stars. And those stars are surrounded by disks of dust and gas, which we call protoplanetary disks. This is the phase where we think there's enough material to actually form things like giant planets, Jupiter analogs. That stage lasts for someone on the order of 1 to 10 million years. There's a large error bar on that, but eventually most of the gas and material is actually removed from these systems. And what we're left with is a main sequence star, any planets that happen to form during this earlier stage, and a remnant belt of material, what we call a debris disk, which is really akin to comets and asteroids in our own solar system. So just to highlight the differences between those two populations, because I'll talk about both of them. On the left, these are protoplanetary disks. These are all the images from the ALMA D-Sharp survey. So pre-main sequence stars, few million years old, rich in primordial gaseous material. I like to think of them as sort of the reservoirs from planet formation. And on the right, these are ALMA images of debris disks, which are now around main sequence stars. They do in fact still have gas, but the picture we have is that actually these are comets that are colliding, and as they collide, they outgas ice. So we're getting secondary produced gas. And so I like to think of debris disks as sort of the fossil record of planet formation because their locations and structures are actually imprinted by the earlier planetary evolution. Okay, so we can study planet forming disks at any wavelength we want. And depending upon the wavelength we choose, we're actually probing slightly different things about these disks. So here are 4 images of the same debris disk. This is AUMIC, one of only a few debris disks known around an M-type star. At the top, we're looking at a sphere image. And when we look at these sort of short wavelengths. We're actually tracing small grains. Sort of the wavelength of light is about the size of the grain you're looking at. So we're looking at micron-sized wavelengths. We're looking at micron-sized grains, where we're actually seeing light reflecting and scattering off of the dust in the systems. This is cool because you can actually see these waves that are propagating outwards in the disk. The bottom three panels are with Herschel, ALMA, and the VLA. So these are all long infrared and radio wavelengths where we're actually seeing thermal emission. So the grains are actually getting heated by the star, and now they're radiating at longer wavelengths. So we can look at these systems and resolve them spatially, but also as a function of wavelength. And by looking at different wavelengths, we're probing the dynamics of different populations of grains. Now, planet formation has had a real revolution in the last decade, largely because of this amazing telescope. So ALMA, the Atacama Large Millimeter and Submillimeter Array, was built in the Atacama Desert in Chile. It came online and started cycle 0 observations the first year that I was a PhD student back in 2011. And ALMA has antennas that can be reconfigured across the Atacama Desert to span up to 16 kilometers. And at that distance, you're probing about 100th of an arc second in resolution, which means that we can take images that look like this, which are the best images of debris disks we had pre-ALMA. So these are all things taken with Herschel, with the submillimeter array on Mauna Kea. Some interesting things, but a lot of blobs. Not going to stand up here and give you an entire talk about blobs, because now we have ALMA, and all of these have been resolved into these beautiful structures. So you can see things that look like blobs have become rings and multiple ring systems. We see warps, we see eccentricities, we see this whole wealth of structure that we now get to try and model and explain. Okay, so that's planet formation. And I said I was going to talk about not just how to form a planet, but how to form a habitable planet. So what do we mean by habitability? So we astronomers like to have a very simple definition of habitability. We define a habitable zone as the distance away from a star where I can plop a planet down. And if that planet is Earth-like, meaning it's Earth-size, it has a magnetic field, it has an Earth-like atmosphere, it will have the right temperature to have liquid water on the surface. So that's simple. If I move a planet too close, gets too hot, all the water is going to boil off, we'll get a runaway greenhouse effect. If I move it too far away, everything's going to freeze. And this is something we can observationally test. But habitability in reality is a lot more complicated. If I really say I want to think about the habitability of like Earth, what is it that makes Earth a habitable planet? It's not just its distance from the sun. It's a bunch of other factors, right? I care about its atmosphere, how much atmosphere it has, what its composition is. I care that Earth has a magnetic field and a molten core and plate tectonics. And technically, in the history of our solar system, there's 3 planets that have been or will be in the habitable zone, not just Earth. There's Venus and Mars, and only one of them has humans on it that are sitting in a colloquium. So clearly, we're missing things if we care just about distance, right? Venus is just a little bit too close, and it had this crazy runaway greenhouse effect happen. And Mars is just a little bit too small. So its core completely solidified, which means it lost a magnetic field, and it was able to have its entire atmosphere stripped by the solar wind. So there's a lot of other factors that we really like to get at if we're going to say we actually want to know if a planet is habitable. If I go and I look at an exoplanet and I say it's in the habitable zone, it might be habitable, but I don't know of any of these other things right now, and so I can't tell you that for certain. So I'm going to start by going into kind of 2 of these factors and ways that we can look at planetary systems without looking at specifically the planets themselves, but the rest of the planetary system to try and answer those questions. So let's start with maybe what seems like an obvious question. Do other planetary systems have giant planets? We've discovered more than 5,000 known exoplanets, so we were getting pretty good statistics. So maybe we should be able to answer this. Okay, so this is the typical exoplanet plot showing mass as a function of period, and it's color-coded by detection technique. It's out of date. This probably only has like 4,000 something exoplanets on it instead of the 5,000 something we know now, but the patterns still hold. Most of the exoplanets we've discovered are through either the radial velocity or the transit technique, and they both are biased towards finding larger planets and planets on much shorter orbits. So there's this huge pileup of planets here at periods much shorter than Earth's period, right? We're populating the inner parts of solar systems a lot. Here's where Jupiter, Saturn, and Uranus are on here. Neptune is out here as well. And you will notice there's nothing there, right? There's this entire part of this diagram where half the planets in our solar system live, and where we actually do not know whether there are exoplanets that have similar orbits and similar properties. And a lot of the reason for that is that we haven't known about exoplanets for long enough to sit around and actually wait for one of those things to transit. Because if something takes 40 years, 50 years, 60 years to orbit, we're never going to be able to detect it through the transit method. Okay, so that's a little bit bleak, but I think that by looking at planet-forming disks, there's actually another way of doing this, which is that if you imagine a large planet sitting out in its disk, it's going to gravitationally sculpt that disk. And you might expect it to introduce lots of structure, things like warps or eccentricities or rings that are actually being introduced in the disk by the planet, which we can observe directly. And to motivate that that's not a crazy statement to make, here's two examples where that actually works. The left is Beta Pictoris, which is a well-known debris disk and has two directly imaged planets in it. Beta Pictoris b is imaged here, and it's actually on an inclined orbit. It's warped relative to the outer disk. And as a result, it's warping the inner part of that disk. And so in this case, we can see the structure and also see the planet that's producing the structure. And we can in fact see this in our own solar system as well, right? The solar system, the Kuiper belt, is a debris disk. So Neptune, in the early history of the solar system, actually migrated outwards, and as it did that, it basically swept a lot of the Kuiper belt into a confined narrow belt. So if you look at the classical Kuiper belt, which is shown here in red, it's confined between two orbital resonances with Neptune. So this holds together here as well, right? We see these orbital patterns in our Kuiper belt objects, and we know that Neptune exists because we live in this solar system. Okay. So let's look at a few other debris disks and see what structure we actually are able to observe with telescopes like ALMA, and how we can maybe interpret that in the realm of planet formation and planetary systems. So this is Fomalhaut, which is probably one of the most well-imaged and famous debris disks. It's around an A-type star, and it's about 450 million years old. And it was first imaged by Hubble. Everybody called it the Eye of Sauron because it's got this like nice look in this orange color scheme. And it in fact had a potential detection of a directly imaged planet, Fomalhaut b. But then the follow-up observations showed that Fomalhaut b was on a very weird orbit, which couldn't really explain the eccentricity of the disk itself. And then even further observations showed that Fomalhaut b just disappeared. And so maybe Fomalhaut b isn't a planet, but it's actually a dust cloud. So we went and tried to map this system with ALMA to look and see not where these small micron-sized grains are that can get scattered by lots of processes, but to look for where the larger millimeter-sized pebbles are in the disk. So this is the first image we got with ALMA. So this is a mosaic image. We actually had 7 pointings with the telescope that's stitched together, and we get this beautiful image of the disk. This is where that potential planet is, maybe question mark. And what's particularly noticeable in this image is that the disk is obviously eccentric. So the pink cross here is where the centroid of the disk is, if you just like drew where the center of this system is. And this is actually the star detected with ALMA. So there's a visible offset between the two. We have actually now done a lot better. And so my grad student, JHD, has been working on this busily. We have a brand new ALMA image with even higher resolution, which lets us look at this in much higher detail. Okay, so what is interesting besides this is a beautiful image of a disk? So one thing was, if you look at this image, you will see that the disk is brighter here at apocenter, which is the side farthest from the star, than at pericenter, the side closest to the star. And that may be a little bit counterintuitive because this is thermal emission. The dust is getting heated by the star. So what exactly is going on? So this was the first disk that we ever observed this in, but it was a theoretical prediction of something called apocenter glow. When we look at planetary systems at shorter wavelengths, things are optically thick. So we're actually most sensitive to the temperature, which means we see things in like Herschel images and brighter at pericenter, closer to the star, where it is in fact hotter. But when we move to ALMA, the disk becomes optically thin. And so we're actually most sensitive to the surface density of material. And because things move slower at their apocenter side, Kepler's laws, we actually see a surface density enhancement at apocenter in eccentric disks. So sort of a nice proof of, theory works here. We can actually, in this new image, do even better than that. Because depending upon whether it's a planet that's actually shaping the orbit of this material, we would expect in the sort of planetary, simple planetary sculpting picture to have the elliptical orbits actually nest. So you end up with a common pericenter point, and then the orbits extend outwards in apocenter, which predicts that there should be a width difference in the disk between apocenter and pericenter. So we shouldn't see the disk have an even width all the way around. We should see the disk narrower at one point than the other. And so what I'm flashing here is not a whole beautiful image, but just the apocenter and pericenter sides on top of each other. So you can see that with the new ALMA observations, which have a resolution of an AU or a couple AU, we are actually able to see that the disk has a noticeably different width and surface density profile between the two sides. So we can actually observe that effect for the first time. Okay, so that's a disk with an eccentricity in it, which could be carved out by a planet, not Fomalhaut b probably, but a Fomalhaut b that we haven't detected yet. What about rings? Yes? Yeah, so we wouldn't expect to detect the planet with ALMA because there's not enough emission. If it was a dust cloud, you could detect that with ALMA. So we can place a really stringent limit on like the potential mass of dust, basically because we don't see anything. Then if we assume that it is some particle distribution, we can say it has to be less than some mass. But there's nothing detected in the ALMA images that has any clear indication. There's a new JWST image of Fomalhaut, which is actually quite interesting as well, and shows that in fact there's an inner disk in this system that's resolved now as well. And there's a few kind of interesting features which we are busily working to compare between the new ALMA image and the JWST to see whether, I think some of the stuff that's in JWST we actually see in the ALMA image as well. But Fomalhaut b remains a bit of a puzzle. Okay, so let's think about rings in disks. So this is another Hubble image of a disk called HD 15115. We have great names for disks. Most of them are just numbers and stellar catalogs. So this disk was famous in the Hubble image because it's actually not the same radial extension on either side. You can see on one side of the disk, it extends much farther than on the other side where it's kind of truncated. So no one was quite sure what was happening. And the best explanation was actually that this disk was ramming into the interstellar medium. And as it hit the interstellar medium, it was causing some kind of ram pressure stripping effect where you were actually like truncating the side of the disk that was hitting and then stripping grains off the other side. And this works well-ish if you have a particularly dense clump of the ISM and you're looking at Hubble where you're seeing micron-sized tiny grains. So we imaged this with ALMA. And it looks nothing like the Hubble image, which was a surprise. So here is the ALMA image overlaid as contours and then as a separate image here. And it shows none of the same asymmetry. And instead it looks quite blobby, right? This looks like a bunch of little blobs. Okay, so here's my primer on looking at disks. Not everybody looks at disks all the time. So you can imagine your debris like a donut, right? And if we have a face-on donut, like here with sprinkles, if I pick any line of sight in this donut, I'm going to see the same amount of material all the way through. So I would expect to see sort of even contours of emission. It's an optically thin donut. I probe the entire surface density. Now, if I take the donut and I tip it, or I incline it relative to my line of sight, if I pick a line of sight through the middle of the donut, I'm going to get donut whole donut. But if I pick one on the edge, it's going to be donut all the way through. So you actually say that you should predict to see these sort of like what we call onsci, which are brightening, limb brightening on the edges of your disk, where you're actually seeing the entire disk all the way through, and like a less emission in the middle part where you're actually probing the inner cavity. Okay, so why did I show that? Because what you actually should see in an edge on disk is these sort of like onsci, these brightening blobs of emission. So in this particular image, we see the star in the middle, and then we see two blobs with a noticeable depletion of brightness in between them. And so the best interpretation we have of that is that this is an edge on disk, but it actually has the star, an inner ring, and an outer ring, and then there's a depleted gap in between. So we can model that and try and actually place some constraints on the size of the gap and use that to then think about what might be opening it. So in the sort of analytical approach, we fit for the radius of the gap, the width of the gap, and the amount of depletion, so the depth of the gap. And then we can use that to actually infer a planet mass, assuming that there's a planet that's opening this gap at the edge of its chaotic zone. And that gives us that there should be like a 0.2 Jupiter mass planet in this gap in the disk. And then what I'm showing on the bottom are actual rebound simulations, which are n-body simulations, where we take now a 0.2 Jupiter mass planet and we plop it at that location in a disk that has the same properties, and we see what happens over 1 million years. And in the 0 eccentricity case, we do open a gap in that time period. And you can play with things a little bit more and change the eccentricity. A slightly eccentric planet actually opens a broader gap in the same time. But plausibly, the scenario holds together that there might actually be a planet in this gap that we could potentially detect. Okay, so eccentric disks, ringed disks, what about systems that might have both? So this has been sort of my recent interesting disk, HD 53143. And again, I'm showing you the original Hubble image, which looks actually quite terrible. If I showed this, you'd probably like, I don't know, maybe there's a disk here, maybe there's not a disk here. So this was originally interpreted as actually some kind of face-on disk that has blobs in it. And so we're seeing these clumps of emission from like resonant clumping in the disk. That's probably a bit of a stretch given the quality of the image. So we imaged it with ALMA, which looks nothing like the Hubble image again. You're starting to see a pattern. The micron-sized grains and the millimeter-sized grains are not doing the same things. So here again is the star and the disk, and noticeably this disk is even more eccentric than the Fomalhaut image I showed you earlier. And then we were like, okay, that's funky. Let's go back and look at it again with Hubble. So we took another Hubble image, which still looks nothing like the ALMA image. So the millimeter and the micron-sized grains are clearly actually doing something completely different in the system. The ALMA data is best fit by having an eccentric ring where the ring is actually very flat. So you can kind of think of disks as having a thickness to them. And in this case, the disk is completely flat, confined to the midplane of the system. The Hubble image is best fit by allowing the disk to puff. So actually having a vertical thickness to it. So that would indicate that there is some kind of eccentric belt of cometary material, and that then the smaller grains are getting produced and kicked up into some fluffy disk that is not actually as eccentric. Okay, we then modeled the ALMA data. And so what I'm showing here is the data, the model that we fit at full resolution and image like the data, and then a residual map, which is where we take the model and subtract it away and see what's left. And we're fitting just a simple eccentric ring model here, where we have 10 million particles, we calculate their orbital positions, and then fit a model like that. We do the fitting in the visibility plane because don't fit to your image ever. Good primer and lesson, right? Because the native data we get from ALMA is in the complex Fourier visibility space, and that is where your inherent uncertainties are. If you move into the visibility, into the image plane, you've lost that. So what we do is we actually basically create the model in the image plane and then sample it onto the visibilities, compare visibilities in an MCMC and iterate. So that model looks very nice. But when you look at the residual map, things start to get a little more puzzling because these are 6, 7 sigma contours in the middle. So there's a lot of residual emission that we're not actually explaining with this simple eccentric model. So I've put these black dashed lines on here as the inner and the outer radius of that outer eccentric disk that we are fitting, which shows that most of this residual emission is coming from inside. And the best interpretation we have is that it might actually be a second disk, because what it looks like is sort of an inclined inner disk where we're again seeing those sort of like limb brightening from the inside. It could also be that there's some dust somehow getting dragged in, but we see this sort of symmetric peak on either side of the star. This was a lovely artist impression that NRAO made for me because we haven't actually resolved this well. We have a new ALMA proposal that will get higher resolution observations, which could actually resolve this inner disk, but it's an interesting system because it means that there's something that is, actually opening a gap and creating an outer eccentric disk. But then if this really is an inner disk and we fit it, it fits to have a different inclination. So it would mean that there's two disks, but they are mutually misaligned from each other. Okay. So if I showed you 3 examples, right? But we've looked at many other disks, and all sorts of disks have structure. It's basically like every disk we look at seems to have some kind of funky structure. And if we then go back to this plot, right, I can start plopping down the hypothetical planets that we infer from these structures in disks. And we're starting to actually populate this side of the plot where Uranus and Neptune and Saturn are that we are completely missing. And there's a new survey that I'm part of called ARCS, which is a large program with ALMA to actually go and image 20 debris disks with high resolution. And I'm sure it will yield much more structure, and we'll have many more plots on this. So it's an intriguing story, right? Like maybe we have a way to probe the outer parts of planetary systems by looking at disk structure. I like that story. It would be great, but I have to always put a caveat on it, right? Because there's lots of things that create structure that are not necessarily planets. In earlier protoplanetary disks, what gets talked about a lot are like chemical gradients and ice lines and things that can cause you to see structure in disks that have a lot of gas, have optical depth effects. These are debris disks, so they're older, so they are optically thin and they don't have much gas. So we've simplified things somewhat, but there are still other things that can produce structure. So here's an example of one thing, which is something called an inclination instability, which is basically allowing self-gravity to take over. If you have enough particles in the outer parts of these disks, you can actually excite this instability that causes you to produce these sort of wave structures in the disk. And so this is showing, going through time, that you kind of kick off this wing and then it actually like flaps over time. And I show this as an example because here's another lovely debris disk that we call the moth, because it has a wing structure. The dust is actually in this kind of extended halo. And you can create that by putting a planet on an eccentric orbit inside the disk and like exciting small particles into this halo, or you could create that doing this. So sometimes it's a little hard to kind of firmly say this is definitely planets when there's other dynamical effects that could be at play. Okay, so I'm going to take an abrupt turn and talk about stars now, because the other half of my research group spends most of their time thinking about what is going on with this bright point source in the middle that I have so far just ignored. And why would we care about that? Because stars, like our sun, are active, and that means that they flare, where they send out bursts of high energy radiation, and they also launch coronal mass ejections, which are bursts of charged particles. Both of those travel out into space and they hit your planet. On Earth, we have a magnetic field, so we're mostly protected, but some come in through the poles. And when that happens, those charged particles actually ionize molecules in our atmosphere. They split them apart, and this is why we see aurora. So when there are periods of higher auroral activity, they coincide with periods of higher solar activity. And it's lovely. We get beautiful displays of light. But most of our host stars for exoplanets are what we call M dwarfs, which are much more magnetically active. And they send out bursts of charged particles and high energy radiation that are hundreds or thousands of times more energetic than our sun. And it starts to kind of beg the question of, are these planets actually habitable? Now, most of our work in stellar activity has traditionally been in the optical, which is where we have telescopes that can do lots of high cadence surveys, and we can look at lots of stars, and we can see these light curves over time. But stellar flares are complicated beasts, and they have different wavelengths of light actually trace different parts of a stellar flare structure. So here's our kind of canonical flare picture, where we have magnetic field lines that actually thread into the surface of the star. As the stellar surface moves around, those lines get twisted. They build up magnetic tension, which snaps eventually. We release this outburst of high energy radiation and charged particles, and they reconnect into this nice loop structure. The foot points, the base here, is where that magnetic field line threads into the surface. And we typically see sort of optical X-ray radiation from that location, where we're actually getting heating. So energy has been propagated down into the surface of the star, and it's now heating and creating a really hot black body. This upper part of the loop, we actually get synchrotron or gyrosynchrotron radiation, which we then see in like the radio and the millimeter and the UV. We're actually seeing things getting accelerated around the field lines. So you should expect that if we look at different wavelengths, we're actually going to see a completely different picture of stellar flares. And so if we're only looking at one, we're not really getting the full energy budget or the full story. And to motivate that, this is the sun, spanning only 100 to 1600 angstroms, but it's images of a flare. And you can see the structure is completely different between the different wavelengths, even over that very short range. Okay, so I got interested in stellar flares kind of through the circuitous disk route. Their closest star to us is Proxima Centauri. It has 3 planets around it, one of which is potentially habitable. And there were some ALMA observations that were done to try and look for dust emission in this system because it's a multi-planet system. It should have had a planetary disk at some point. Maybe it has a remnant debris disk, and we can look at this as sort of an analog to our own solar system. Okay, so these are the original ALMA observations that were done. On the left is all of the data averaged together. There was about 13 hours of data that were taken, and what's typically done when we image disks is we just plop it all together. We assume the disk isn't changing on hour-long timescales, and we accumulate data together, right, to get the best signal noise we can. So you can see there is a bright point source here. It has a flux that's in excess of what the stellar photosphere should be at those wavelengths, and so this was interpreted as dust, where we're seeing an unresolved disk, and the excess is coming from heating of that unresolved dust. Okay, so I downloaded these observations, and I was like, let's see what it looks like if I just look at them in a time-resolved fashion. So the middle panel here is if you just take the first 12 hours of data and you average it all together. It does not look the same. There's actually nothing detected in this image at all. That's above a 3 sigma level. And the last panel is if you only look at that last hour, where there's suddenly something extremely bright. So something's changing with time. Now we can actually do better because ALMA has about a 1 second integration time. So if we look at each one of those individual seconds individually, in this last hour, it turns out there's nothing except for about 2 minutes where there's this little period of hiccups, and then there's a giant brightening in the star, and then it fades back down. And the star brightens from 0 millijanskis to 100 in a period of a couple of minutes. So this was surprising because it was the first time we'd actually detected a flare from an M-dwarf at millimeter wavelengths. We had sort of, I don't know, just assumed that stars didn't really do interesting things in the millimeter, but they do. And we started looking at archival ALMA observations with other stars that are in the center of disks. So what I'm showing here is Epsilon Eridani, which has a well-known disk. So this is just going back into the archival data from ALMA. And you can see there's actually several flares detected from Epsilon Eridani, also originally interpreted as maybe being emission from an inner disk. And this is HD 53143, which I showed you several slides earlier, where we actually had 8 different ALMA observations, and you can see that the stellar flux changes dramatically in that as well. This one was fun because it happened that TESS was observing at the exact same time. So we sort of got this TESS optical light curve at the same time as the ALMA light curve. But clearly, M-dwarfs, solar-like stars, they all flare at millimeter wavelengths. So the question was, how does that actually compare to stellar activity at other wavelengths, right? Because our canonical flare picture is based in the optical, the X-ray, the UV, and now we have the millimeter, but we don't know how they connect. And so I spent quite a bit of time wrangling telescopes to organize a first kind of multi-wavelength observing campaign where we would go and look at Proxima for 40 hours simultaneously with 8 different telescopes. So we have ALMA paired with a bunch of optical telescopes on the ground to do photometry and spectroscopy. We targeted this when TESS was observing Proxima as well, and then had Hubble, Swift, and Chandra to cover everything from the UV out to the X-ray. And we coordinated all these telescopes to actually point at Proxima simultaneously so that we could get simultaneous light curves, and we could see like what happens in the millimeter, how that traces into these other wavelengths. So this was the first result that we published from that. Which shows one extremely large flare. This was the brightest flare we've ever detected from Proxima. This is stepping through in wavelength from ALMA, TESS, DuPont, where we're looking at H alpha and helium-1, which are two known flare tracing lines, and then Hubble. And this is just zooming in on just the ALMA and the Hubble data. And there's a few interesting things to look at here. One, this thing brightens by a factor of almost 15,000 in the Hubble data. And each of these points is 1 second. So the entire flare lasts for 8 seconds total. That's it. In 8 seconds, it goes from 0 to 15,000 times brighter and then back. The optical data is actually noticeably delayed relative to the millimeter and the UV data. So the millimeter and UV data are almost perfectly in lockstep with each other. They brighten and fall at the exact same time. And the optical data actually peaks several minutes later and lasts for quite a bit longer. So we see optical emission until like minutes to half an hour after the initial flare, but that initial burst that we see only in the UV and the millimeter. Okay. So this is intriguing actually, because it starts to kind of put a picture of where different wavelengths relate to each other. Yeah? No, no. This was the biggest one. And so we sort of like put it out as like a demonstration of like, look, it wasn't totally crazy to give us 40 hours of your telescope time. The rest of the papers are going to be coming out soon. We have them almost done. We've detected tens and tens of flares. Proxima is extremely flary. My student, Kiana, just made the first what we call flare frequency distribution at millimeter wavelengths, and we detect like 500 flares in the ALMA data in 40 hours. In 40 hours, yeah. Some of them, many of them are very, very small. They're not beautiful light curves like this, but we detect a flare, many flares every hour. So what has typically been done in the community is to use optical data and then infer these high energy fluxes, because the stuff that actually does damage to atmospheres is the UV and the X-ray. This to me sort of suggests like we should think about that more carefully, because the optical and the UV are not actually tracing each other well. Maybe the millimeter and the UV trace each other better, but clearly the optical and the UV emission are produced by different mechanisms, and they are not actually that clean of a relationship. And I can make that point better by looking at this in sort of a cumulative rate distribution. So these are flare frequency distributions, so it's number as a function of energy or amplitude. And these are all of the optical flares that were observed from Proxima with TESS and a telescope called the Everyscope. So really energetic flares are over here on the right. Really tiny flares are up here. And the green line is where that flare is. That brightens by a factor of 15,000 in the Hubble data. Is the biggest flare we've ever seen from Proxima with Hubble, but is actually a tiny, tiny, tiny flare according to the optical emission. Flares of that size occur basically every day in the optical, and it's like in the 75th percentile of tiny, tiny flares. Right, so what's weird about this flare is that we observe all these simultaneously. And so in the Hubble data, this is the brightest flare we have ever seen from Proxima with Hubble. Like it's enormous, it's a huge energy. But in the optical, it's tiny. And there are many, many, many more flares from Proxima that are way more energetic in the optical. So it's oddly small. And when we look at the cumulative data set, there are instances where we see optical emission, but we actually don't really see anything in the millimeter and the UV, and many times where we see UV and millimeter emission, but we actually see nothing at all in the optical emission, not even a small flux. So there seems to be quite a decorrelation between like when you see strong optical emission and when you see strong UV emission. So the optical data from TESS and from most of these is like a red kind of photometric bandpass. Typically, the best for flares is to go towards the red because we're looking at these M dwarfs. The Hubble data is all, we use STIS, so it's spectroscopic data. The purple, like the pink color here is silicon-4, which is a flare line. The kind of blue-purple color is what we call the pseudo-continuum, which is basically we took all the interline areas where there weren't strong flare lines and like looked at just the variation of the continuum flux level, which is actually even more interesting because it's that pseudo-continuum that really brightens a ton. And during this peak flare, you see the Hubble data actually has 2 peaks here. There is almost no line emission in this initial one, And then the line emission peaks later when the optical emission actually peaks. That is a good question. There are multiple interpretations of that. There have been, like for UV data, people usually claim it's some combination of like a hot black body and synchrotron emission. And then there's some split between the two. The millimeter data, which I can show if we jump right to here, right? So with ALMA, we can actually look at not just the total flux, but because we have a spectral bandpass and we have the XX and YY polarizations, we can look at its like spectral dependence and get a lower limit on the linear polarization. And so this is that flare. This is the original Proxima flare, and this is a flare from AUMIC. And what we see is that actually as you go into the peak of the flare, there's this change in the spectral index that's quite noticeable, where it becomes this sort of steeply negative spectral index. And this is a lower limit, but there's some evidence of polarization. Radio emission from flares is usually assumed to be gyrosynchrotron or synchrotron, so it is kind of logical given that in the millimeter we're seeing synchrotron emission as well, but we're seeing a different part of the spectrum, so we're getting a different spectral index out of it. And then if the UV and the millimeter are so in lockstep with each other, then maybe what we're seeing in the continuum is some kind of synchrotron emission in the UV. But we need to do this for even more stars, right? So this is Proxima, and we're working on finishing that up. And now we've done this for 5 more nearby M dwarfs to sort of try and like see how this builds as a sample, and whether it's just Proxima being a weirdo, or this is actually a consistent picture for more flare stars. Okay. And so this is highlighting another result from that paper where we actually have X-ray data. So I just showed you UV. So this is Chandra observations. This is actually quite a small flare, which was nice because it's small. We can actually compare it directly to solar flares. So this is sort of looking at kind of traditional Gödel-Benz relationships to compare how like the X-ray to radio fluxes during quiescence and flare compare to what we think they should. And what's puzzling about this is actually that the millimeter emission seems like overproduced in this M dwarf flare. Like it's consistent in quiescence, but it's not consistent in the sort of flaring moment where there's just a ton of millimeter emission, more than we would have predicted. And what we've now done is actually get JWST observations. So this is TRAPPIST. This is like the light curve of TRAPPIST-1 as measured by JWST, which, great exoplanets, but this looks problematic, right? Because, there's a lot happening here. TRAPPIST is flaring constantly in the JWST observations. But we can use that data to say some really interesting things about flares. So this is actually taking this large flare here with nearest and splitting it out by spectral wavelength. So this is H alpha, helium, Paschen lines. We have bracket beta. And so all of these lines are excited during the flare, and we can actually see differences in like when different lines are excited and use that to sort of say something about the physical model of what's happening in the flare. And for the first time, we're able to make a flare frequency distribution in the infrared. What's interesting about this is the blue are the points from JWST. The gray is what was assumed to be the flare frequency distribution of TRAPPIST. They are not the same at all. So what we were assuming by taking the optical and converting out to the infrared was very much wrong and very much under-predicting what we think the flare rate should be. And now if we actually measure it with JWST, there's this huge boost in terms of the energies of the flares, which sounds really bleak, right? Because obviously we'd like to look at TRAPPIST to look at the planets. The nice thing is that actually if we use that and we use the fact that these different lines are getting excited, we can fit like a spectrally resolved model to the flare and then remove it from the transit light curve. So these are showing the transit light curve, pre-removing the flare where things are terrible, and then removing the flare in this spectrally resolved model template and actually cleaning up the transit light curve. So the flare is really interesting from a flare perspective because we've never looked at flares in the near IR, but then we can also make the exoplanet light curves better. So there's hope for our exoplanet atmospheres. Okay, so I'm running out of time. So I wanted to sort of end by saying, like, where do we go from here, right? Like there's a lot of cool things and some things make some sense and some things are confusing. So what would we like to do next? So from a flare perspective, I've been working on this mission called SPEX, which is the Early Star and Planet Evolution Explorer. And the goal here is, wouldn't it be nice if instead of trying to cobble together a whole bunch of telescopes and get multi-wavelength observations, if we just had one telescope that did multi-wavelength observations, and we could do a bunch of campaigns where we point at young stellar regions, look at a ton of stars in them simultaneously, perfectly, with these multi-band photometry. And so SPEX is focusing on doing optical and near UV to actually like be able to get a simultaneous UV and optical light curve for a ton of stars. And then I'm also doing some work to try and actually, I can hand wave and say, this is really bad for exoplanets, like these giant flares, they're gonna kill all the life on these planets, but we have never really done the work to prove that that's true. So we're doing work now to actually input these flare frequency distributions into exoplanet models and specifically look at oxygen production in atmospheres. Because one thing that can happen is if you dissociate a bunch of water molecules, you can end up overproducing oxygen in atmospheres by just having a ton of flares. And so it throws into question whether oxygen really is a good biosignature or not. And then we're actually working with a geneticist at the University of Minnesota to then try and like recreate flares in a lab with a UV flash bulb and look at whether that does damage to DNA or not, which may or may not work, but is at least an attempt to try and like quantify whether UV radiation is really as damaging as we think it is. Okay, so coming back to this, right? I've touched on a few things. There's a lot more. A few things that I think are really critical and I have so far glossed over, and we actually don't have that much information about, is what is the volatile abundance that actually goes into these planets in the first place? And how do these planets actually get water? Because it's great to think about atmospheres getting destroyed and life forms getting zapped by UV radiation, but if you never get volatiles and water into the planet in the first place, that whole research question is, kind of moot. So why do I highlight those things? Disks are complicated places, and this is my cartoon picture of a protoplanetary disk and a debris disk, sort of highlighting the different temperature regions and the flaring and the different chemical ratios as things freeze out at different heights and distances in a disk. Each wavelength we look at is good at probing particular things. So ALMA is most sensitive to really cold material in the outer parts of disks. So it's great at looking at Kuiper belts. And it's great at looking at the kind of like large cold molecules like formaldehyde and methane. But we are sort of missing the intermediate areas, and we're missing a lot of lines that would be especially useful to answer questions about volatiles and water in disks. And it turns out that the place that all those lines are is in the far IR, where we have no telescopes that function at all right now. So we just cannot do the science. Which is why I've been spending a lot of time in the last year writing a proposal to NASA to try and build a far infrared telescope. So it's called FIRST, the Far Infrared Spectroscopy Space Telescope, and it's targeted at having extremely high spectral resolving power so that we can do this sort of science. And why would that be interesting? So for one thing that I'll highlight, we have a very nice picture of planet formation, and I can show you tons of images of disks, but we actually don't know how massive those disks are. So this is one disk, TW Hydra, which is probably the best studied of all protoplanetary disks. And every single point on this plot is a measurement of its mass. This is a logarithmic scale. It spans orders of magnitude, right? Why is that? Well, most of the mass in disks is in hydrogen, but we cannot measure hydrogen because the transitions don't get excited because disks are too cold. So mostly what we do is we try and use tracers like CO or dust mass or something else, and then we model it back and infer the original hydrogen mass. So all of these lower points here are doing that. And we get orders of magnitude different things depending upon the assumptions we make, because clearly we don't actually know those tracers that well. There is a molecule that's much better. TW Hydra is the only disk for which this has been done because Herschel happened before ALMA happened, really, and so we didn't have a lot of overlap between the two. So this wasn't an interesting research question then, but we looked with Herschel and looked at TW Hydra and measured a molecule called HD, which is deuterated hydrogen. which is pretty close to hydrogen. So there's a lot less extrapolation and leads to having much better determinations of the mass. We can actually do even better with HD because if you have high enough spectral resolving power, you can actually look at the profile of the line and do what we call tomographic mapping, because these lines are getting broadened by the rotation in the disk, right? The Keplerian rotation. And so depending upon whether your line is inner or outer part of the disk, you actually see different profiles in the line. So here's a bunch of models of HD in like a solar minimum mass solar nebula disk by varying the inclination and by actually putting a gap into the disk or not. If you put a gap in, you actually lose the high velocity wings of the line because now you've removed all that high velocity material from the inner part of the disk. And so these two lines of HD are in the infrared, the far IR. So we can't look at them in JWST. We can't look at them with ALMA. We can't look at them with anything. But if we had a telescope that could do this, we could actually go and do large surveys and for the first time be able to say what the mass is of these planet-forming disks. And that's a pretty fundamental question, because if we don't know that, like, I can't actually tell you whether we can form these planetary systems or not because we don't know the mass. Yeah. Sorry, I could not hear you. Oh, I mean, so like there is still some abundance correction there, but that has been much better like chemically modeled and understood. So there's some scaling factor that you apply to scale whatever you measure in your HD mass to a hydrogen mass. There is some uncertainty that we can never actually get rid of there, but it's a lot better than the CO to hydrogen abundance ratio. Okay, and so then to highlight one other area that we're completely missing, right, which is water. So this is the histogram of water transitions as a function of gas temperature, as a function of like wavelength. So you can sort of think, you know, these are gas temperature bins, but this is shorter wavelengths, longer wavelengths. For cold water that you would expect in star and planet forming regions, there's only one line that JWST can actually look at. And there are 3 lines accessible to ALMA, which are almost never actually observable because we live on a planet with a water atmosphere. So we can almost never look at them. And the rest of the transitions of water are entirely in the far infrared. They're all between 30 and 600 microns. And right now, that means that we basically can't actually look at water abundances. We can't measure water in comets. We can't measure water in planetary disks. We can't measure water in star forming regions. Water was one of the huge science cases for Herschel, but Herschel sort of only started doing this in star formation and didn't really get to do it in planet forming disks. So another huge area that we can do things is to like look at water lines and HDO lines and measure things like the D to H ratio and look at how water is actually processed and inherited from star formation into planet formation. And so those are at least a few of the reasons why I think we really need a far infrared space telescope, because we are missing some large chunk of our knowledge of how to form a habitable planet, and without it, we're never going to actually fully answer that question. Okay, so I will leave up some take-home messages, and then I'm happy to take more questions.
Okay, so we've got about 5 minutes for questions. We'll be at the back first there.
Different flares or for different wavelengths to have different, well, I can address a few things. So one thing is, I think that in this sort of canonical flare picture, we naturally would say that different wavelengths should behave differently, right? Because if we have this loop structure and we have synchrotron emission coming from the upper part of this loop, and then that has to actually propagate down the loop into the surface to actually cause the heating, it is maybe not a huge surprise that we might see synchrotron emission first, and then we might actually see this kind of black body emission happening later. Then I think that ultimately that's a simple picture of flares. And now that we are looking at flares with a much higher time cadence, you know, we had this very simple model where everybody looked at flares with sort of coarse time cadence, and we saw a peak and then this exponential decay, and that was sort of assumed to be what all flares look like. You get this like emission, like sharp release, and then this kind of slow decay down. When we've gone back and looked at the same flares, because tests had originally like a 2-minute cadence, and then it got its 30-second cadence, suddenly the exact same flares looked much more complex, where you see multiple peak structures, you see pre-flares and post-flares and light curves that don't actually have this decay. So I think actually the physical structure underlying it is probably more complex, right? I think people talk about having arcades of loops where you actually have not a single loop that's breaking, but a chain of loops. So you can produce these much more complicated looking light curves that are going to behave totally differently because you have different amounts of loops actually breaking in different physical structures.
In the previous, you said there's not much gas, but it's a little more quantitative. I mean, is there enough to make a dynamical difference?
Yeah. So that is a good question, and it varies wildly. I'd say on average, the masses of debris disks in dust are on the order of maybe an Earth mass, and the masses in gas are sort of like a lunar mass to a few Earth masses. So these are very mass limited systems in general. But there are some number of debris disks that have quite large amounts of gas compared to the dust, where if you actually look at the gas to dust ratio, it's comparable to a protoplanetary disk. So that is puzzling. And so I say, like, we think it comes from cometary collisions, but if you actually look at the entire population, there's a few systems that clearly have so much gas that the rates of cometary collisions become bizarre. You're saying, like, I have, 1,000 Hale-Bopp comets colliding every day to produce that much gas. And so there are other pictures. There's some models that actually predict that you could maintain gas from the protoplanetary disk phase by having some kind of photo-dissociated region that actually like self-shields gas and maintains some of the original protoplanetary disk reservoir. And that might mean that you have enough gas to be interesting. There is in fact one system, HD 32297, where if you look at the velocity of the material, it is rotating sub-Keplerian. So it seems like there's some kind of drag happening from the gas, and it's one of these systems that has a ton of gas. That's a sort of new area because prior to ALMA, we had never detected gas in a debris disk, and we just said debris disks don't have any gas at all. They're just dust. And now there's a whole population of disks that seem to have quite a bit.
What are the challenges for building these far-infrared space telescopes? Does it have the same issues that JWST with the temperature, having to cool down everything?
Oh yes, anything in the infrared has a huge problem with heat, right? Because infrared is heat radiation, and if you do anything that's like hot or put it near something that's hot, you no longer can do your science. So the far IR is interesting. It does need to be at L2 and it does need to be cryogenic. But what has happened basically is that, originally with Herschel was a great telescope, but it wasn't that sensitive. So you didn't care about some of these things as much because the detectors were not very good. And so they weren't background limited. So if it was a little bit warm, it was okay. But there's been a huge advance in detectors for the far infrared now. It's probably like the area of astrophysics where like detector technology has advanced the most, because now we have these things called transition edge sensors and MKIDs, kinetic inductance detectors, which are quantum detectors, and they are extremely sensitive. And so this is like a challenge, but also a really cool thing, because if you could launch these things into space and actually cryogenically cool them, we can basically change the sensitivity of the far infrared by several orders of magnitude with the same size space telescope as Herschel, just by changing the detectors.
Great, and we're on the hour now, so there might be some more questions. Our speaker will be around at the IIS this afternoon and also at Peyton tomorrow, so hold them for then. Before we leave, just to point out that the call lunch will now be going on in Simon's Hall, so we've got more to look forward to. And so yes, let's thank our speaker once again.